So Danny, what you know? Do you mind Danny or Dan?
Daniel or Dan?
Okay, Dan.
Yeah,
right,
Danny
Dan.
is when I was 8.
All right, Dan. So what is this here?
This is also part of the thermal patent. It's these are LEDs for light arrays. Basically, modular array to replace general lighting, agricultural lighting. This one's for we were setting it up for agricultural lighting for a greenhouse. Greenhouses that we're building, a self-sufficient greenhouse.
Okay.
This is
how many watts?
this one running. I'm going to turn it on. It's going to totally screw up your camera, but it won't hurt your camera. But it's just hard to see. That's about 30 volts. It's about 15 watts, right? So you got half an amp and about 30 volts. But it doesn't get hot, and
not at all.
I'm going to turn it on off so you can actually see some of it. All the thermal action happens between this top layer and that piece of copper. This is an insulator. We don't want heat to go back because typically lights are embedded in something, right? So if you embed your fixture into a ceiling, and you're having your thermal energy move in that direction, eventually it's got nowhere to go. So the way this is designed is, since the LED, which is your light source, is also the source of the heat, I've created it so it sheets across, kind of like dumping a bucket of water in a fast-moving, a bucket of red paint, let's say, in a fast-moving stream. Disperses very quickly. If I have to put a big heat sink on it, it's kind of like dumping that same bucket in a slow, big pond. It's just going to sit there and sink away. Well, it doesn't give any benefit to the LED until it can finally dissipate all the way out. But that LED is cranking it out very quickly. So it's relative to the frequency of the amount of energy that's coming out, thermal energy coming out, and how quickly it can be moved away so it doesn't affect the PN junction, the positive negative junction of the semiconductor, which is actually its process is emitting a photon, right? So there's a curve. As that PN junction heats up, the amount of light that's generated is diminished. So there's an efficacy point where a little bit of thermal energy will give you a little bit of a voltage drop that doesn't affect the efficacy. It actually can increase the efficacy if it's balanced right. But after that, it's a knee curve, and it just much like a solar panel. Over 25 degrees C, you're starting to have diminished results. So semiconductors are very sensitive to thermal energy. They work better the colder it is.
Okay.
Heat sinks, not the best idea, because you're really talking about something that's thinner than a human hair. That's your heat source. Having a massive metal behind it, not a really great solution, because
it takes a long time to get
absorb all the way through. Exactly.
Yeah, you're only as good as your weakest link.
So as I did for the heating and cooling, it's the same. The HVAC system. Same thing. Look at it from a relative scale of the application. How does it relate to the actual system that it's in? Because we've built these systems for humanity to live in, but we haven't really taken advantage of the technologies as a whole and looked at the whole system, right? So that's really where my patents.
All right, so tell me about the patents quickly.
So the patents look at basically all the built environment systems that we created over the course of the last 200 years, and the technologies that we've discovered, not only in the past 200 years, but even recently, and how we've taken some of those technologies and kind of just shoved them into an old paradigm instead of re-looking at the model.
So that's what you've done.
That's what I've done. I've actually looked at the entire system and said, wait a minute, this is not the best way to handle this application, right? For this. So for example, our wheelbase for cars, is based on Roman chariots. right? Because when they built the Appian Way, if you were going to make a wagon and you didn't make it exactly the same base as the Roman chariot, your wagons went down the road like this, right? So what I've done is looked at technology as a whole, and I was an architect since the first. I had my first design. I designed when I was 15. It was built when I was 16, and when I was 47, I stopped to fix systems. So I've got a lot of buildings on the planet. So I understand the systems, and I looked at them and thought, okay, this has got to change. This has got to change. This has got to change. I thought the LEDs were going to change immediately because I figured the guys that actually understood the physics behind the electron giving up some energy would, basically push that knowledge forward. But what happened is the industry used to buy lamps for fixtures. You would just buy a bulb, right? And it was an incandescent bulb or a fluorescent bulb, which is basically a wire of gas. So they weren't semiconductor guys that started making fixtures, right? So now the industry has to kind of understand a little bit about thermodynamics. They have to understand electronics. It used to be a filament that got hot. So
So now that you're keeping this thing cool, which is one of your main points here, you're increasing the longevity by how much?
Oh, well, that was I sent a chart out to Nietzsche, and they can't run the test that long because at the rate that we're running these chips, the amount of years or hours, it was over 10 million hours. Well, I can't even say that.
Okay, how about weather? I'm using this for billboards on the outside. You can. How about applications for billboards?
If you see the screens that are along the strip that are LED LCDs, or LED display billboards, most of those are Nietzsche chips. Same technology as this. They're outdoors, gets rained on. Hell, it probably got snowed on this morning because we have snow on all the low mountains today, which is rare. But that's really not the part of the semiconductor. That's basically how the fixture's made. The fixture right behind you, same technology. The boards are that thin. It's very, very thin. It's all empty space inside that panel. We've created that fixture to be a IP66. So, matter of fact, we went a little further.
Okay, you can't even see it. Sorry.
3 feet of water. Yeah, that's 24 watts.
Can you run that one more time?
Yeah.
And I'll describe what's going on.
15 watts.
This is 15 watts, and it just blows it right off my screen. And is that the highest it gets?
Oh no, I can go higher.
I know. So let's see what you can do.
Let me get it to.
So how's this going to save the billboard industry money?
Well, instead of going lumens per watt, because we're at the point where we've had outside independent labs at above 167, we know finished product. We know we can hit above 200 lumens per watt. But at some point, you want to look at lumens per dollar as opposed to lumens per watt, because it just becomes a cost factor. What's more important is the let me switch this to
well, that's really getting up there. You don't have to do more than that.
60 watts.
Well, that's unbelievable. That's unbelievable. I can tell you that standing here, it's extremely bright. And in fact, I'm getting traces on my eyeballs right now.
Yeah, I know. I can.
All right. So, anything else you want to say about this invention?
This one's also ready to move forward. I've got a couple of niche market that we're looking at. One in the film industry because they deal with a lot of heat and they need a lot of light, and another for the agriculture. But this is can be used for general lighting. Going again, I don't want to start a company and do I'm going to be there.
Cost comparison to what's out there now.
These huge margins. If they're again, you're looking at compared to the LEDs on the market, we're about 50% less power.
All right, so you're gonna save 50% on the power.
and our cost to manufacture.
Yeah.
Because we don't have the huge heat sinks, we don't have all that material, and
Right.
shipping costs.
Yeah. Much less.
Much less. Yeah.
Okay. Fantastic. Okay, so Dan, what's this?
So this is the next gen of that light. This is what we do is we built a roadmap for all of the inventions for about 5 years out of what how we expect our technology to be ready commercially over the next 5 years. Actually, the lighting I've done 9 years out. But
Okay.
the next generation of this, this is the parts are only you've got a base plate. This is a thermal isolation, so that the heat does not transfer down. This gets tucked in. Obviously,
What is this?
this is a thermoelectric, so it's the same type of module that's powering the Voyager spacecraft. You don't make electricity. Electricity is a reaction. A thermal difference
Right.
creates a voltage
Right.
that allows an electron flow inside the separate posts, positive, negative, positive, negative. It's a vertical solar panel, basically.
Right.
Right. So by having a thermal difference, the greater that thermal difference, the better the voltage is, the more electrons that can flow if there's a load on it. So
Right.
this gets
I hear you need at least a 15% differential to get electricity.
not really. I can use the table and a little bit of just your metabolism and not a very good thermal connection. You'll see the voltage to get usable. Yes, if you
Right.
usable.
Right. Right. Okay. So
Then again, that's a relative term, because if you can, if you're not don't require a lot of energy, or you require it intermittently, it can harvest and be stored in, say, capacitors, and then be used later. So, which is
Right.
what we're going to be doing here.
So you pop this in. So now
this will be connected to the circuit that gets printed
Right.
on this. The LEDs get put on, and then this goes over. So all the thermal energy is going to be moving away from the chips to this point. Just by it being there, it acts as a heat pump, right? Because the electrons here want to be able to move. So they use.
So you're
the thermal-
recycling to make.
recycling the thermal energy.
Yeah, recycling the thermal energy goes back into the system and powers and saves energy.
Yeah, basically what it does is what we do is we charge a capacitor that will allow that energy to go out at the right voltage that we
Right.
want. Right, so it just slowly builds up. When it hits that point, it lets it goes into the system and gives us some power.
Brilliant.
And we don't have to use it for that. We can actually use it for other chips that we can print a circuit on the back of the board, right? To do things like Wi-Fi or like a Wi-Fi repeater or Internet of Things. So there's having that intermittent power for sensors like smoke detectors or chemical detectors in a building. You're in that space. You've got the real estate for it, right? So if you think about streetlights, if your streetlight only needed to be this thin, you got all that real estate that every car and every vehicle goes by. If you use the energy that's there, you can have cell towers now not having to broadcast or your own cell phone, not having to go a mile away, right? You've got the ability to have cameras and security.
Well, Big Brother will like that.
Yeah, no, but think about for ambulances.
Yeah.
If you're an ambulance company and you knew which roads had traffic on, you could actually move around. You could actually flash lights now to allow drivers to know that an ambulance is on its way to please start to move over. Right? So there's so much more that could be done when you have smart systems. The drawback of having smart systems before were they needed more power. Not anymore.
Right. Well, I know that the whole LED streetlight business is going to, you're not even wiring it. Each one is localized self-generation with a solar panel.
Yeah.
So, I mean, that's been the trend.
Yeah.
Okay, so I'm going to